Next up, we have Rafal Szarecki from Juniper Networks presenting architecture for fine-grained, high-resolution network telemetry elements.
Hi, I'm the last one between you and the lunch, and it's only quarter. So let's do it quickly. I'm not the first, I have to say. Thank you to Josh. He covered half of my presentation by coincidence. When we think about telemetry or getting data from the network nodes, we are doing that. But we have to be very clear that the actual data appears, they are collected and not in the node, in the atomic parts and elements inside. So when we will talk about a network node, say router, we always have the control plane, we always have the data plane, we also have kind of auxiliary control where we can, when some data are measured. And traditionally, how we do the telemetry today, because we pull the data, we take it over some intervals, which is typically 5 minutes or more. And this way, we obscure the dynamics. We obscure the short-lived events. We just see the network in average. And that's reasonable for the long-term planning, for a slow-moving, slow-changing environment. And the other interesting observation is that what we are collecting today, we are collecting the data we understand. So everybody knows what is the interface packet counter, byte counter, what it means if it goes up and down. But this is not the end of the story. So the traditional way, it's SNMP. And the SNMP is a polling base to get the data. You have to ask for it individually, one by one. Anybody try to code something in ASN1 and create the MIP? That's a pain in us. And the data structure, the MIP is either tree or, thanks God, we have tables. But actual data are the structure, are dynamic, flexible things which describe the objects. So to model it into the MIP, there is a substantial work which has to be done. And then to decode it on the collector, on the management station, we have to do this exercise again. SNMP is also quite inefficient. Even historically was done to be efficient, because in SNMP, every atomic data, every counter, every scalar is delivered together with the full description. There is no concept of the providing this set of attributes for the monitored object. And even worse, sometimes these relevant attributes, let's say for the interface, are located in different branches of the tree, which makes the protocol inefficient. And it doesn't matter at the moment, right? Because if we collect the limited number of data every 5 minutes, okay, fine. Who cares about another 100 kilobits per second now? But just for the record, in typical port counters query, we send 4 to 8 times more description of the data than actual data. And it doesn't include the fact that we have to ask the same way, very specific for every counter, we have to put the whole OIT. So why we talk about the telemetry and the need for the telemetry, and why we use the telemetry? It's because the network industry are entering the new stage, right? I remember 2 NANOGs back, there was a big panel discussion why the networking is not so interesting, not so sexy, why other things are attracts people from the colleges and universities. Well, it is. We just entered the adulthoods, right? We are not, the network industry is not that sexy as it was when I started 95, 96. It's not developing that fast in terms of the new technologies. It's not that we have another protocol every 2 years, as it was in early 2000. But expectation rise. The expectation for the network is to be more solid, reliable, efficient. So I see that the networking industry, I'm not saying about particular network, but as an industry, we're entering the optimization phase. And every optimization starts from the data collection. If you don't have a data, you are blind. You don't know what you can optimize, how much you can optimize, and if you optimize, do you really optimize or screw up something? So we need the infrastructure, we need which allows us to better deal with the short-living events, with the micro-burst things, and which provides the data in runtime, or as close to runtime as possible. Because only then we can benefit from the machine learning or big data analytics to find a relationship with the data. And this comes back to the position today. I want to recall the statement. What we typically do, we collect the counters we understand. But if we collect enough data points, enough counters, and ask the computer networks, artificial intelligence maybe, to find the relationship, find the pattern in the theoretically or on the first look in unrelated data, then we understand how network behave better to the level we don't today. I know it's like an open statement. Nobody did it yet, so it's hard to give example. But if you recall Monday talk of Facebook, they said, yeah, they have this ephemeral traffic which from time to time fills the one of the ECMP link. And over a couple of months of the fighting with the problem, they found that before it happens, there is always some link failure or some topology change in the network. I don't know how much this finding helps them to solve the problem, but this is something which the high fidelity, high volume of telemetry plus big data analytics can give you. End of the day, this is to enable things like usage-based provisioning. Use all the power, all the cycles of the CPU, all the memory we can, or, well, good to keep some margin, but just that margin. And also to proactive reaction or proactive optimization of the network based on the trends. So in this, to get there, we need 3 building blocks. We need to know what kind of the data could be taken from the network elements, from the network. We need to be able to ask the routers to provide what the OSS system needs. We can say controller in these days. And this is pretty straightforward, right? I think the current, of course, we have to define that, but the current tools, netconf, Young modeling is probably, and maybe OpenConfig is probably exactly what is needed here. I will also use the concept later in my talk, concept of the sensor. Sensor is like a thing which sits inside the router, inside the network node, which is aware about objects they are going to measure or monitor, and not only about one of attribute, like one counter, but it's set of counter. You can see the example, right? This interface sensor knows about all interfaces, all counters related to them. And sensors are instantiated where the data actually are measured. So ideally, the interface sensor should be instantiated directly on the ISIC or directly on the NPU. And then sensor is also able to export data. So data in the place, in the point in the system where the raw data are collected, this is also the place when the data are exported. I skip publishing and subscribing part. For the data streaming, exporting actual data from the element, there are either periodical push model or the asynchronous state change driven publication of the state change data. As I said, it's distributed, so where the data are collected on NPU for the data plane or on the control plane for the protocols and other things, this is where the report is generated and sent. And it's not that absolutely new concept. We do this for the flows. JFlow are generated that way, but here the call is to do this for virtually anything. And of course, the way how we export what is on the wire is important because it needs to be efficient on the wire, on the resources. So the cost of generating the report has to be as low as possible. We want to do this from NPU. We want to do this from architecture perspective from ISIC. There is no memory. There is no processing power or very limited. So we have to be very careful about that. And whatever we do, it has to be flexible and extensible. So efficiency on the wire, yes, this means that we probably have to send the data as a binary. It still could be self-describing format. We still could have some information about the data, about the particular counters, embedded into the report. But it has to be embedded in as a binary numbers. And also avoid, we need to avoid sending this, the redundant information. If we report the interface stats, there is no point to send 19 times the name of the interface, and it's enough to send them once, and inside them, maybe not encapsulate, but under the interface, put the all relevant information, and then move it to another interface. What you can see here is actually what we observe in our experiments. I will tell it later. And data modeling. I think the best example is best to explain is by example. We want to, of course, have it unambiguous, vendor agnostic, or vendor neutral. So we try to model the data as let's say, like a graph. That's example for the fabric statistics. The vertices of the graph are general things like ISIC, switch plane. Potentially, we can extend this model to have egress interface for VOQ system. And every edge, this unidirectional edge, is a set of attributes, which tells us how fabric works between two ISICs, or between ISIC and the fabric plane, or from the ISIC to the egress interface when we extend it. And then the data structure follows it, right? So the fabric is described as a set of edges. And each edge has the set of attributes, and these attributes not have to be equal. Same for at every edge. If the given attribute, let's say packet counter, doesn't exist for the edge from the fabric to the packet processor, because there are cells, this counter doesn't exist, but there will be a counter which express the cells. So it's not fixed format. Depending what data are available on given platform, on given context, on given edge, the set of data could be different. Why? Okay, fine. We have this encoding. We have efficient way to deliver the data. We can take it from the various points on the system on the high frequency. It's very light to process. But why we do that? What is the potential benefit? And this is one example. Let's assume that the question is, okay, I have 4 interfaces working. My platform has another 2. I'm not using it yet. But what will be impact if I connect, if I start using it? And let's assume that we are looking at the buffer memory, shared buffer, right? So if I have my high fidelity telemetry, so I have these samples every 2 seconds, or this means that over the week is 200,000 of the samples. And I observe that 44 of them, which is like 0.2%, actually it's 100% of buffer utilization. Probably some losses. Who cares? If I increase my load 1.5 times, 150% time, what would happen? If I have this graph, like a blue one on the bottom, okay, I move them 1.5 times up. And some samples, during this prediction, some samples cross the 100% utilization line. But that's fine. I can see, well, it's like a 0.6% or 0.78%. That's not a big deal. Why it's better than SNMP? Because if I do the same logic with SNMP, but taking the counters every 5 seconds, I still see 44 events of crossing the red line. The point is that this 44% is spread out over whole week, and this 44 events are spread out across the week, and it's not only 44 out of 200,000, but it's 44 out of 2,000. So with the SNMP, the same graph will be like shown on the by dots. It's very flat, very close to the 100% line. If I move it up by 1.5 times, then most of them may cross the line and say, hey, it's another 40% losses, 40% of time my buffer is full. That's not what I want. Same network, same traffic. If your data are not accurate, not granular enough, you cannot do the proper prediction. I will skip this example because in interest of time. And as well this one. Oh. Anyway, the telemetry gives us a data which fits the collector, and this is the collection of the data is not the goal by themselves, right? The analytics, the way how we calculate, how we look at the data, how we try to correlate them, or even better, let the algorithm correlate them. It's like a caravelle. It's for us, for the networking industry, it's something which can bring us beyond the horizon, right? It's like, hey, we can do something new. It's a journey. We may, some of you can start with the telemetry. There is no, we don't know where we go. Christopher Columbus don't know where he go. He thought he'd go to India and he ends up in America, but hey, that was El Dorado. We do some early experiments. It's not that just talk about the theory. We do some early experiments with one company from the content Web 2.0 space. And Google protobuffers are used to create the reports. Why protobufs? They are relatively easy to program. They have support for multiple languages, so it goes well with us to create the sensors, but as well goes well to create the collectors. It's open source. It creates binary format. It creates the efficient way, and this gives us a way to, this allows us to generate the reports at the high rate from the distributed elements in the system. And this experiment was, the couple of sensors was enabled, right? The one sensor was for LSPs. So every time LSP change, go up, down, change the path, the LSP sensor sends the report, hey, there is a new path with new bound, with new requested bound, with new RRO, and do this in real time almost, right? So it's without significant delay. There is no scrubbing, there is no logging to system, there is no parsing of CLI outputs. And our customer is generally using this for like a network state rewind to see what was the LSPs in the past at a given moment of time, and for bandwidth demands, like a trend analysis. The other sensor was interfaces, and it's like thousands of, we experiment, we did like 1,000 of ports, 19 counters each, 64 bits each counter, so it's quite significant thing. And the reports was sent every few seconds. So every interface, 19 counters every few seconds, and there was 1,000 interfaces. And we had independent, the sensor for the interfaces are distributed. They are run on the line cards of the system. So the central control plane was like even not aware about load related to this generation, this data generation. And because these line cards, we have multiple sources, we have also some kind of smearing of the report, even the interval was equal, because each line card runs at generate the report at different time. The purpose for it, yeah, at the moment is just general performance management, but on the short intervals to better see how dynamic is the traffic, how they are changing. General findings. We was able to do this interface statistic gathering, and as I said, we decrease the interval to some level of 10 seconds without any impact on the router. Router doesn't notify that it's something going there. There is no high load on the CPU or the line cards. And time needed to collect all LSP statistics across the not statistic, LSP states, right? Because we talk about the changes of the states and path, was also reduced by order of magnitude. And it was relatively simple because there is no need for scrubbing, right? There is no opening the netcon for SSH session and taking the CLI outputs, then parsing. The data was provided straight when the change happens only, and with the proper, and only the data needed with the proper structure. So, telemetry, the better telemetry, we call it next generation, but the better telemetry is critical because we enter the optimization phase with the networking. We need more data to have our network working more optimal, to better use gear and devices provided by this or other vendor or open or white boxes, doesn't matter, right? We want to use them as much as they can, to use all resources, all capabilities network provides. And because the network devices, network scales out, then we have more devices, and also scale in. I'm coming from vendor. I can say that yes, there will be a bigger boxes with more line cards, more I6, more gear inside. This means there is more objects which you want to monitor. And these two things happens together, so we have like a magnification effect. We need something better than SNMP to work with the scale. And I not say that telemetry will replace the SNMP in the foreseen future. There are things which are, SNMP is there, right? And building the models for everything SNMP develop or MIP has since, I don't know, 20, 30 years. I think 1988 was the beginning of the SNMP. So this will take time. So we talk about augmentation. This new architecture, new technology for telemetry is more to augment SNMP when it's needed for the scale or for high fidelity. And the last but not least, more data and more sophisticated data analytics is something which yet to be discovered. The benefits of it, it's yet to be discovered. It's like, journey behind the horizon. We don't know what's there, but the things is there. We just don't know that it's there. Thank you much. Everybody wants lunch? No questions?
So, thank you very much. Starting back here in the Grad Ballroom at 2:30, we have our peering track. There will also be 2 tutorials taking place. Krasi is doing Denial of Service 101, taking place in the Tower Salon A, and Matt Ringel doing Whiteboarding 101 in Colonial. Also, our general sessions will reconvene here at 4:30. Thanks.